Alright, so I got the thumbs up. I think we're ready to go. So thank you guys for coming. We're definitely the coolest talk that I'm here. So my name is, that's me, I'm Michael speaking. And I was just saying, I work for Atomic Object. We are a development and design consultancy. So we have designers, developers, we have operations people, about 50 people, and we work out of Grand Rapids. Also satellite office in Ann Arbor. So we don't have any projects of our own. And one of the things that's really cool about that is we do actually a surprising amount of greenfield development. Get to do a lot of new stuff and set up the stack again and reflect on what's been working on it. SQL is something that we use a lot. And I mean, we, as some people also, we, as an industry, despite having been standardized back in like '92, before many of the languages and platforms we use today, it's still the data store of choice for damn near anything, it seems like. So I think it's a little worth talking about. So, if you notice, this is a total shameless ripoff of Bruce Eccles' Thinking In series of books, with, I hope, much the same idea. Everything I'm telling you today is going to be wrong. Nothing is going to be perfectly 100% accurate, because I'm a database user, not a database implementer. But I hope that it'll help you build a mental model that gives you some good heuristics and able to make good decisions about what your applications are going to do. So, as I said, SQL is the backing store for a lot of our apps, but I really rarely use SQL. There's only one project where I'd say I use it directly as a primary thing. We use an ORM, we use Active Record, Subsonic, Hibernate. Some of them are probably way out of date right now. We use these things, and they kind of warp our brain. But you start thinking about it in the way that your tools think about it. And that's okay. That's easy trouble with sometimes. So, I have two sections I want to cover today. So I want to talk about how to think about SQL joins, that I think we tend to oversimplify. And I'm going to dig into how to index things effectively. So I've actually timed this pretty closely. I think I've got between 30 and 35 minutes worth of material. So do feel free to jump in and make this conversation. I think that'll work out really well. Let's dig in. So first, SQL joins. So, quick review. Inner join is saying, I have a set over here and a set over here, and give me where they pair. Left join says, give me all of this stuff, or actually, for you guys, give me all this stuff, and any pairs over here. Right join is the reverse. So we get that, and we regurgitate that definition. But we tend to think about it much more like this. This is out of the Rails documentation, actually. We can say that, we can give a definition of join, but we think about it as, it's just a hash map. It's, I connect things to dependencies. But when we think about it like this, and I think that's a really imperative way to think about it. Like this makes sense if you're writing a form. And that is what your database is doing down application, SQL, implementation, like way down here, that's what it's doing. But you're not down here, way up here. So I think you should turn it around. This is how I think about it. Now, in a second, get into the distinction. But I want to point out, I think this is a much more declarative way of doing it. And so you should do all the things and then filter on the condition. This really opens you up, I think, to new kinds of queries. So here's a quick little example, just a warm-up to kind of wake us off. So this is saying, who haven't we invited to the party? Maybe we just want to make fun of them for not being cool enough, or we need to send them an invite. And so I think this is an illustration of the kinds of theories that you miss when you think about it as a has negative. Because what we're doing here, we're looking for the negative. We're making an outer join. I said left join, I should have said left outer join. And then we're discarding all of those records that joined. So I think that's kind of interesting. I'll come back to this again a little bit later. I want to give you a new, little more sophisticated example. So, at Atomic, we all write for the company blog. Everybody makes a post for your inquiry. And so this is a question we might want to ask. It's pretty reasonable. And it's a question that comes up all the time. What is the latest blog message from each device to show on my dashboard? What is the most popular post, the most recent, the most expensive car in each class? This kind of max of subgroups problem is pretty common. And so I want to apply a transformation to this. Oh, sorry, I'm jumping ahead. So it's easy to answer this for one. You can do this. And if we're in Ruby, I'm using numeral, I can do .map or .each. I can run that as a long time. If I'm in C#, I can use link, same thing. But that obviously is terrible because I'm running 5, 10, 1,000 queries. But it's easy to understand, so that is a plus. But okay, so I reworded this. This is the same transformation I talked about at the beginning. It's take it and go, don't do the imperative thing. Think about it, declare it in a way where we get a description of a condition that can apply across the board. So first, do you at least believe me that these are equivalent? Not everybody's got their coffee. I agree. It's okay. Okay, so they're equivalent. So here's the thing with that. That should look like a joint. Who we're describing, we have a table of blog posts. And records in there have some kind of relationship to records in this table of blog posts. That happens to be the same table, but it doesn't matter. I can join the table to itself, no problem. So I'm going to build up this query from the English. And don't worry if you don't follow it, because this is nasty and it took me a lot of work out on paper before I really understood it. And I'll break down in a minute. But first, this part up. I want some blocks. And I want them where there's something more popular. So I want to point out this inequality. So this is what I was saying. We just want to make pairs where a condition is true. Any condition, such as an inequality. It's not just a dependent record. And that's where I think your has-many kind of definition really gets in the way. They can be compound conditions. They can be compound conditions as well. And of course, we want ones that don't have any more popular. So we can filter those out. So there we are. So go replicate it. Go and do like it. This is terrible, right? Kind of is, but why? I think this is a key thing. So I have a hypothesis for why this is not obvious, and why it's so hard to understand. Joins are not fundamental. If I was doing arithmetic, 1 plus 1 is a fundamental operation. It's easy to understand. Multiplication is kind of repeated addition, but it's still like an atom on its own. Joins absolutely are not. So this, I pulled this from the Wikipedia page on relational algebra. That's the definition of an integer. So it's a little bit awkward, but you can see there's like a thing happening here and a thing happening here. So there's like 2 operations. And this is where I decided when you get down into the implementation, it starts to feel a little bit more imperative as we talk about implementation. So to translate it to English, pseudo-English, I made up this syntax. It doesn't exist. If there were no ORM like this, I'd be pretty curious to see what it would look like, but there isn't. But this is equivalent. I took the 2 mathematical operations that we saw a minute ago and turned them into something that looks like function calls. And now it's really clear that there's at least 2 operations happening. So that's why an inner join starts to get a little bit. outer joins are just awful. So that's why it's not obvious. That's the outer joins definition I'm going to keep. So I'm not going to try to unpack that, but I do want to point out there are at least 6 separate operations happening to make this work. I'm not actually sure if it's implemented like this in the generic way, or if they do something smart down underneath the hood. But in any case, that's why I think our intuition doesn't always match. So we're here. So let's try to unpack this. What happens first? We have a lot of things going on. Any guesses of what happens first? Okay, that's pretty fair. But it's not obvious. And I think, like when I'm doing arithmetic, I have an order of operations, right? I know what happens first. But that's just notation, actually. Like I can do addition before multiplication and it's legal. Well, it's the same thing here. Like these things can happen in different orders, but we've written it in a particular notation, and the database is going to implement it in an order. But we have no parentheses, so we don't know which. Personally, I would rather this look like list. Maybe I should. So I made up a syntax. In fact, I made up an order of operations. Now, if you search for this on the web, you can find something. They'll tell you that your from clause happens. But my from clause here goes from here to here, and this stuff, and that's in there. So what happens first? So my order of operations is this. I start with my joins to do the Cartesian product. So note what I've highlighted. I haven't highlighted the condition. So I described the definition of an outer join in 2 steps. We do the Cartesian product, and then we filter. And then you do where clause, and that actually covers this query. But then you have our group by if you have grouping. If you're doing having clause, you do that. If you're not selecting everything, you do that. But these things, I think, are pretty straightforward. These behave in a way that our intuition matches. I think. So we have an order of operation. I think now we can start to understand that query. So before I go too much further, thoughts, reactions? How are we doing so far?
It seems similar to like map reduce.
You know, I think there's probably some truth to that. I think, like, map doesn't quite follow that. You're not really doing a transformation like on a single element. You're doing it on a combination. You need a join. But I think that is a good way to think about it. We're going and blowing things out big and then reducing that set. So I think it's actually a really good analogy. Okay, so there's our query. I just shrunk it a little bit to fit. And I'm going to execute it. Now, there's a data set. Now that is intentionally quite terse because I'm going to show you the Cartesian product, and it's going to take up the whole screen. So here we go. So remember our problem. We want the most popular post for each employee. So that's going to be these 2. So this first one, he's got 2 posts, and that was the most popular. Number 2 here, you've only got 1, so that's what we want. So order of operations, step 1, do the Cartesian product. And so I've taken and blown things out. We've got all of the employee 0 ones matched to everything else. Matched to nothing, matched to himself, matched to whatever else. And the same for the other ones. Next, let's start filtering. So our join clause is multiple filters. I'm going to attack this one at a time and start with the employee. I'm going to point out here, actually, I think your database probably does actually start here. If you are doing this query and you have an index on employee ID, there's good odds it's actually going to pick that one to start with. Because that's going to reduce the set from considering joining this to everything to a much smaller set. And so these rows that I've grayed out here and point out the arrows, Those are ones where the employee didn't match. We're going to drop those. Next, we got some rows where things were not more popular. Depending on how you word it. So those get dropped. And now this is where I do a little handling. This is why I threw in the definition of join earlier. I don't have a great way to demo this, because I don't want to show 6 operations. That first one is joining joining a post with the nulls. So remember, it's an outer join. We'll get nulls if there is no match, and if there is a match, we don't get that null row. So that one gets dropped. Hard to show in this kind of file. We do our where clause. And I've got all that other stuff that doesn't apply here. And pretty quickly, we're down to the 2 rows we called out earlier. So that's kind of my fundamental lesson I showed. And I think that ends up being really powerful. One example of it that I used was I wanted to compare summary data for companies according to their fiscal year for a client. And one company starts in March, one starts in January. So what I did is I had data that I rolled up by month, and I had a summary table that I blew out, and I joined it, and used the join to create a Cartesian product, so that it was a year as if it started in January, and a year as if it started in February. So intentionally creating a Cartesian product, and then not filtering down to just our matches. I'm not going to demo that. My point being that, like, if you understand that those operations are happening, I think it opens up the door to a lot of interesting queries. Feel free to jump in anytime if you have any questions. And I'll move on. What do I got? So if you actually have to do this query, write this instead. This Postgres supports these window functions, so you can actually do like kind of partial group buys, which is really cool. This, I think, doesn't provide as interesting an example, so I didn't use it, but this works. For Postgres, you can also do this, which only works for the top, if you only want the top 1. If you want the top 3, you gotta go and do this. But if you do the simple thing, this works really well, and I think it's semantic, like in the sense you can try to do semantic CSS. This is semantic SQL. It says, I want posts distributed by employee according to these. I think it's really easy to understand what's happening here, especially if you have that crazy inequality join dropped in the middle of a bigger query. It can be hard to unpack. So I think this is a good lesson. Go look at your tools. I don't think MySQL is anything like this, because MySQL is like broken and backwards and really missing the features. Oracle has its own features and brokenness. Postgres has its own tools. And they change a lot on different versions. So seriously, check out your tools. They're probably a good way to solve your problem. But the fundamentals are there. Okay, so before I jump topics, here's that first query. And so really quick, using data order operations, we can understand this a bit more. We start here, making the product. We filter it to the pairings and the nulls. And then you drop everybody that wasn't invited and select people where that worked. So I hope that makes a little more sense now. It didn't make sense before. Okay, so this section is going to be mostly disconnected from the previous. It's just another thing that I think is really important. Indexes make things faster. Except that they don't. You can't just up an index everything. So I want to show you a little bit about how indexes work, how they don't work, and how your database decides what indexes to use. So I made up this definition, which I think is a reasonable heuristic again. And it gives you some idea of what's going on. So an index is a redundant copy of your data. So you added however much more disk space to store it, and it has to be kept up to date. You may sometimes, but you're probably not indexing all your rows. There's only partial, but you're usually doing it for all your rows in a table. And this is why it's in a useful order. Okay, so here's some data. I used did just a random data generation there. If we wanted to query it, like this is not a hard thing for us to answer. We can go, we query the data. But these are not sorted by last name. They're sorted by probably on disk order or something crazy like that. So if this were 1 million records, we would not be able to do this manually. So we make an index. Say we index last name. So this is straightforward. It looks like this. There's all the last names in order. Now, even as a human, I can answer that question. I can go and do a binary search, and I can find that person. And then we do an indirection back to the table for first name, gender, and date. All those columns that we don't have in the index. So that automatically gets you at some of the key things. I do want to point out, it's not just gross. It's going to be probably a B tree or some fancy data structure. But it's designed for looking things up in a sorted sense. So all your computer science-y data structures class stuff, there's probably something like that under the hood. But if you think about it like this, that's a good heuristic. So here's a different example of querying this index. So here, you'll note I have the last name I'm looking at. And I'm looking at gender. Gender is not in the index. So this will get us pretty far. It'll be looking at the index. It's going to show us 2 rows. And we're going to have to do an interaction back to the table for each of those rows. And pretty quickly we'll filter it to the one row we want after we examine all of the tables. So this is where I want to introduce my core principle for indexes. I describe this as wanting a prefix. We'll get into what that means in a second, but your columns in your index are ordered. So if your query doesn't have something that can be put in that same order, then it can't use the index. So it's pretty obvious here. That's not going to help you. Because I'm looking at first name, I have an index on last name. I've got to just scan everything. What's less obvious is this. If I have this index, where I have an index on last name and then first name, this still helps me not even a little bit for this query. So, my examples, an index on first name, last name might look like this. I made a mistake here, I should have this be the same. But anyway, again, it's probably not a naive binary tree, it's probably like a B plus tree or a red black tree or whatever. But I think if you look at it like this, it's a little more obvious. So if I'm searching for something like this, I can pretty clearly see that I'm going to go and do typical tree traversal looking for it. So it's going to just transform that. So like I got both these columns in the index. So I'm going to look at things that match that. I'm not sure if it actually concatenates it. I mean, it obviously knows where one column starts from. But I think it's a good way to think about it. If you do that in your head, you'll know whether or not your database is going to be effective. And here, it is. It walks down the tree. And it's a lot more obvious now. How would this tree help you with that question? So here's a few examples. Let's see if there's anything interesting. So I got first name, last name. This is why I said prefix match. First name? Yeah, it's still great. That's going to help us a lot there. First name and last name, that's good. This here, that's pretty cool too. If you got even a partial match, it can use that because they're still in an order that's useful. But if we're just looking at the last name, it's not going to help us any. This one I think is interesting. It will use the index for first name here, but because we have this wild card, it can't help us at all with the last name. It's just going to grab all the B things, regardless of the last name of the index. It probably will save and not do the indirection back to the table, but the inherent order doesn't naturally help. So, quick digression. You usually do create index on default first name. But you can sometimes do other stuff. And this is really cool. In Postgres, for instance, you can do expression indexes. And this is something I haven't done yet, but I'm actually really excited about the possibility. Because it means if you have any kind of expression that evaluates, that's square root, you could index the result of that and not recalculate it for every row as later. Where they get really cool for me, I think, is the new Postgres version 9.4, 9.5, one of those, introduced JSON as a column type. You can now index into your JSON columns. Because you can say, I don't want to index a column. I want to index the column, this key, this property, index 5 in the array. And it will go and grab that for every row, maintain that in index, which I think makes it actually really, really feasible to do most of your data in a much more relational, tabular, highly structured way. And if you need other stuff or something flexible, you can probably call that in. Okay, so this is the big question of index. But I put an index on it. Why doesn't it like me? Well, I know the reason why it doesn't like me, but everybody else. So the way it picks indexes is by it guesses. It looks at a lot of ways to do the query, and it picks the cheapest. Duh! That's why it's not doing what you thought. I'm going to tell you a little bit about how it does that estimation. So here's our example query again. Now, if it's not using index, it can do it like this. It's just going to scan the table and look at matches. And so it actually can estimate a cost because it knows how much it costs to pull a row off this. It has a decent idea how many rows it has. It may not always know exactly, but it knows if you have 10 records or a million. So it does some multiplication. And for our data set, that's all. So here's a different strategy. Let's index last name. And so it looks kind of similar. We're going to scan the index, and then we're going to hit the source table. But it's actually a much different equation. Because what we see is now we got to look at stuff for the index, which is going to be some kind of still disk reads, or maybe memory. And we've got a different estimate because this is not a sequential access. This is like B-tree traversal. And then we still have to go back to our source table. If that's that indirection I talked about. But this is probably still cheaper for this query. So why is it 1? Well, the answer is because it actually knows a lot about your data in a kind of summary format. So different databases are going to do this differently. This is Postgres. I set up the same data we saw a second ago in a table. And this query, that's in their docs. So if you go look at the search for PG stats table, you can find this one. And there's other interesting columns here. But this is what it knows about our table. So I want to point out 2 columns. It's looking at data for every column in my table and tells me, I don't know what that means actually. But it's going to tell you maybe what the most common values are. And then it's got this kind of distinct. This is the most interesting one to me. So in Postgres, this can be a positive number, which would be just the exact number of distinct values in the table. It doesn't have to know what the values are, but it knows there's 5 distinct values. It can use that to make inferences. When it's negative, it's just a description of a proportion. So last name, that -1, that says that for every row in the table, there's a unique value for last name. Which means if I do an equality at last name, I know only one row is going to match. So my B tree, like I know it's log n at best, and you get 1, and I can get a million of them back. Gender is a different equation. We had, I think, 8 rows. 3 of them were male and 5 were female. Maybe I can first. But so that's not a totally crazy ratio. That says for every 5 rows, there's 1 distinct value. So if I got about roughly 10 rows, I got 2 values, that makes sense. So we can make a guess case. Different query. So, again, if I'm not using the index, it scans things. So this totally the same. Because it's got an index, it's got to look at the table, no difference. But if using the index, now because this is an inequality, it knows it's going to get more than 1 record. So now it's plugged in a different number range. And so in that case, it's actually going to prefer the full table scan probably. It might have some other guesses where if it knows, like I don't know if it keeps like standard deviation of a table. I think as a human, I could use that to make inferences and say that, well, if that's a few standard deviations away, then I can guess that I'm not going to get it. But in general, it doesn't know a lot about specific segments. It just knows about common values. So in this case, it's erring on the side of scanning. If you made it an equality, it would absolutely use the index, because it would know that that's going to get it down to a single unit drive.
Does Postgres have covering indexes? Does it use it?
I'm not sure how to read its explain output as well as I do with MySQL, but I think it does. So to summarize, the covering index as I understand it is if your query is only asking for something that's in the index, and or you're asking for example, all columns, but all columns are indexed, then it actually never has to do the indirection. And because it knows what your query is, it can make that estimate. And so I use that to good effect by essentially keeping two copies of the data in different orders. So I can look at it one way for the main source data, and I can look at another for this one particular query. Now, those are big, and they're expensive to maintain, but if it's heavily read and not often written, that's worthwhile.
Well, the reason I ask is SQL Server has, well, the newer version of SQL Server has the include function to create an index. So I can specify what my index lookups are based on. So obviously SQL Server has the clustered indexes, which is how it's physically stored, and it has non-clustered indexes. To avoid what we call in SQL Server terms a bookmark lookup, which is where I get a non-clustered and then have to go back to the source table. It used to be in SQL Server, what we handled it was, if we thought, like, instead of doing a select star, if we knew we only going to use these 4 columns for, say, 75 to 80% of our queries, we would make sure that that non-clustered index had every single column, as long as it didn't exceed the maximum size limit for a column. And then, but nowadays, what we have is we have the ability to specify all the indexing on, and then specify includes, and what SQL Server will do is it'll throw the additional columns in, it just won't index on them. So like if I know that I'm always going to search on first name, last name in that order, but I also know that I'm going to return date of birth and gender and everything else, I can tell, hey, include these other 2 columns, and then I will get that first cost, that index read cost times that.
Okay, but I just got the 5-minute warning, so I don't want to go on it too much. But I'm curious, what is the difference for doing that versus just indexing? Because the rows are still like in index order. So,
well, the thing of it is, you have to remember that SQL Server does use a B tree, but as it does a B tree, it also does a double linked list across each of the rows or each of the levels, right? And so that's how it does its range query really fast. So if I keep my indexes relatively small, especially when I'm doing queries that pull back a lot of records, then it can say, okay, I only need to pull this segment and read from this next segment, stores it in and displays its query, as opposed to having to go and so the reads actually end up being smaller overall. That's the reason it does.
okay, no, that makes sense. That's pretty cool. Yeah, I haven't done a lot of SQL Server work, so I haven't done any of that functionality. But I think that is another good pointer to the lesson. Understand your tool. So let's see, I got like 7 slides left, so let's see. Talk about this. Okay, so gender was interesting here because gender was not a distinct value. So if you had an index on last name and a separate index on gender, how would it get? Well, for last name, we know we only get 1 row back. For gender, it scales proportionally according to that value we saw in that table. And so this is going to be a bigger value. It's probably going to pick the index on last name. I've seen this data generally prefer to index things that have higher cardinality. So if you have gender, an index can only get you down to roughly 50%. If you have an active flag, well, if everything's active, that doesn't help. If you have 10% active and thousands of archived records, then that might be really valuable. But think about how it's going to reduce your data set walking that straight. Yeah, see, there we are. So that's the stuff we covered. And I want to point out these 2 websites. These are all written by a guy named Mark something. And he actually does dig into some of the more specific on this data structures. He has opinions on clustered indexes. He doesn't seem to like using them very much. I'm not going to go into that. And I also want to point out modern SQL. I made a reference early on to SQL 92. I may also point out things like the rank over partition. Things have changed. Your basics are good to know, but we're 20 years on. So go figure out what your tools can do. There's a lot out there. And in my opinion, for whatever opinions are worth, I honestly would never use a NoSQL database to start with. It may be useful down the line, but with knowing how to query things effectively, the good tooling that exists with JSON columns and expression indexes, I see no reason to start. You need it later, great, yeah, but I wouldn't start there. I have a lot of opinions. Not all of them are good, but so that's me, and that's my contact information. Feel free to send me a note. I got like the 5 business cards I can stuff in my wall if anyone wants to talk. Otherwise, if you just want to kick me off the stage, I'm cool with that. Okay. I'll be around till about 2 o'clock, so I'm happy to have a conversation. So, any thoughts, reactions?